Hello and welcome to week 3. This week we're going to cover polar coordinates, conic sections and three-dimensional Cartesian coordinates. Last week we talked about Cartesian coordinates in 2 dimensions, how we could describe the position of a point in the plane using 2 numbers, an x-coordinate and a y-coordinate. But there's another way to describe the position of a point in the plane. We could use polar coordinates. Instead of using the numbers x and y, we could use the numbers r and theta, where r is the distance from our point P to the origin, and theta is the angle between this blue ray and the x-axis. When we measure the angle, we need to know which way we're going. Are we going clockwise or are we going anti-clockwise? And we have a system. When we're going anti-clockwise, we say that the angle is a positive angle, we use a positive number. If we measure an angle going clockwise, then we have a negative angle. You can imagine polar coordinates like this. Let's suppose we have a ruler, and let's suppose we put 0 at the origin. And of course, let's suppose this is a special mathematical ruler which also includes negative numbers. And let's suppose we take this ruler, we always keep 0 at the origin, and let's suppose we rotate this ruler. For example, let's suppose we rotate our ruler anti-clockwise by 45 degrees. Then we can measure the polar coordinates for all of the points along the ruler. For example, this point, the distance from the origin to this point is 1, and the angle of the ruler is 45. So we say this point has polar coordinates 1, 45 degrees. The point which I'm pointing at with a red arrow has polar coordinates 4, 45 degrees, because the distance from this point to the origin is 4. And the angle that the ruler makes is 45 degrees. We can also go the other way along the ruler. We can look, for example, at this point, which I'm pointing at with a green arrow. Again, the ruler has made an angle of 45 degrees, but this time, because we're going in the opposite direction, we say that this point has polar coordinates -2, 45 degrees. Or let's suppose we rotate our ruler in the opposite direction. Let's suppose we take our ruler. Again, we always keep 0 at 0. And let's suppose we're going to rotate this ruler clockwise by an angle of 30 degrees. Because we're going clockwise, we say that the angle is a negative number. So we're measuring this angle as -30 degrees. And then again, we can write down the polar coordinates of the points along the ruler. For example, this point, the distance from this point to the origin is 3, and the ruler has been rotated by -30 degrees, so the coordinates of this point are 3 -30 degrees. This point, for example, with the orange arrow, we're going the opposite way along the ruler, so we say the distance is -1 and the angle is -30 degrees. There are more than one way to write down the polar coordinates for a point. For example, think about this point P. We could say that this point P has polar coordinates 2, 30 degrees. The distance is 2 and the angle is 30 degrees. But let's suppose instead of rotating our ruler anti-clockwise 30 degrees, we rotated our ruler 330 degrees clockwise, or through an angle of -330 degrees. Then our ruler would end up in the same place. So we could say that this point has polar coordinates 2, -330 degrees. And this is true. The polar coordinates 2, 30 degrees is the same as the polar coordinates 2, -330 degrees. What about this point in red, the point P? One way to calculate the polar coordinates of P would be to rotate our ruler 210 degrees, and then we would find that +2 on the ruler lines up with this point. So we could say that the point has coordinates 210 degrees. Or we could rotate our ruler just 30 degrees, and then we would find that -2 on the ruler lines up with this point. So this point also has polar coordinates -2, 30 degrees. Let's suppose we're asked to find all of the polar coordinates of 30 degrees. To start with, we have a choice. We can either rotate our ruler so that +2 on the ruler is on the point, or we can rotate our ruler so that -2 on the ruler is on the point. In other words, we can either have r is 2, or we can have r is -2. First of all, let's think about r is 2. Then we know we can have 30 degrees. We can also rotate our ruler through an extra turn. Instead of just rotating through 30 degrees, we can go all of the way around another 360 degrees. We could have 30 plus 360 degrees. Or we can go around another turn, and we'd end up with the ruler in the same place. We could have 30 plus 720 degrees, or go around another time, 30 plus 1080 degrees, etc. Or, instead of rotating around 30 degrees, we might choose to go the other way. We might go clockwise, and in this case it would be 30 minus 360 degrees, or minus 330 degrees. Or we might go around like this. Go all of the way around and then around again. That would be 30 minus 720 degrees, etc. There are infinitely many ways to find the angle. Next, let's think about r is -2. If we have -2, it means rotating the ruler by 180 degrees. So whichever angles we had at the top, we should have that angle plus 180 degrees, because we're going all of the way around to the other side. So we would have 210 degrees, or 210 degrees plus or minus 360 degrees, or 210 degrees plus or minus 720 degrees, etc. So the answer to this question is the point with polar coordinates 30 degrees has polar coordinates 30 plus a multiple of 360 degrees, or -2, 210 plus a multiple of 360 degrees. We can talk about drawing the graph of a polar equation. For example, draw the graph of r is equal to a. This means that the distance from the graph to the origin must always be the same, must always be a or minus a. In other words, the distance from our graph to the origin must always be the absolute value of a. So we get a circle. Draw the graph of theta equal to b. We're going to have a line, because all of the points on this red line have the same angle. They have the angle of b. Now, because r equal to 1 is a circle of radius 1, and r equal to -1 is also a circle of radius absolute value of -1 or 1, these are both the same circle of radius 1 centered at the origin. And because 210 is 30 plus 180, and because minus 150 degrees is 30 minus 180 degrees, These are all equations for the same line. Draw the set of points whose polar coordinates satisfy the following two rules. First of all, r is between 1 and 2. Theta is between 0 and 90. Just as we did last time, we're going to pick out the information. First of all, I'm interested in r equal to 1. We know that's a circle of radius 1. So roughly, I will draw it like this. R equal to 2 is also a circle, and this time a radius of radius 2. Theta equal to 0 is the x-axis, this line. Theta equal to 90 is this vertical line. We are asked to find all of the points which are between these. So between the red circle and the orange circle, and between the purple line and the green line. So we're going to be asked to color in this part. And it's neater if I draw it with a computer. Draw the set of points whose polar coordinates satisfy the following. R is between -3 and 2. Theta is equal to 45 degrees. This time I'm going to do the angle first. The line of 45 degrees looks like this. On this line, r equal to 2 is about here. R equal to -3 is going to be down here. We're asked to draw the set of points that satisfy all of these rules. We must be on this dashed orange line, and the radius must be between -3 and 2. So we're going to have something like this. Again, this is neater if I draw this with a computer. Draw the set of points whose polar coordinates satisfy r is less than or equal to 0 and theta is equal to 60 degrees. If you're rewatching the video, pause it now, try to sketch it yourself, and then click play. I'm just going to show you the solution. Draw the set of points whose polar coordinates satisfy the following. Theta is between 120 degrees and 150 degrees. Again, if you're rewatching this, pause the video here and try to draw it yourself. This is the solution. We have two systems of coordinates for describing the position of a point. We can use x and y, or we can use r and theta. And we have some simple equations to convert one into the other. From this picture, you can see straight away that x must be r cos theta, and y must be r sin theta. Or by Pythagoras, x squared plus y squared must be r squared, and from trigonometry, tan of theta must be y divided by x. I've put these equations at the top. For example, convert the polar coordinates r theta equal to -3, 90 degrees into Cartesian coordinates. We use our equations. We want to find x and y. We know that x is r cos theta and y is r sin theta. Go through the calculation and we find that xy is equal to 0 minus 3. Find polar coordinates for the Cartesian coordinates xy is equal to 5 minus 12. Remember, there are infinitely many polar coordinates. This question just asks us to find one. We could choose to have positive r, or we could choose to have negative r. Just to make this easier for me, I'm choosing to have r a positive number. Then, using the equation r squared is equal to x squared plus y squared, we can find that r must be 13. Then we need to find the angle. There are 3 equations containing the angle. I'm choosing to use r is equal to r sine theta. Or in other words, theta must be sine inverse of y over r. Put the numbers in, put it into our calculator, and we get approximately minus 67.38 degrees. So the answer to this question is 13 minus 67.38 degrees. Just to check that we haven't made a mistake, it's worth drawing a picture. Here's the point where x is 5 and y is minus 12. We calculated 13, that looks about right. And we calculated that the angle should be minus 67.38. On the picture, that looks about right. We haven't done anything silly. Chapter 9 is about conic sections. So imagine we have a double cone. We can imagine we take a bit of paper, we roll it up to make a cone like this, and then at the bottom we put another one. And I'm interested in cutting the cone in different ways. First of all, let's imagine we cut the cone horizontally using a horizontal plane. I'm interested in what is the red curve that we get when we cut across a cone horizontally. And the answer, as you can imagine, is a circle. We know an equation for the circle: x minus h squared plus y minus k squared is equal to a squared, where hk is the center and a is the radius. What about if instead of cutting horizontally, we cut at an angle? Let's suppose we cut at a shallow angle like this. What is the shape of this red curve? The answer is we have a shape called an ellipse. What if we cut at a steeper slope? I'm going to draw a quick picture here. If we drew a 2-dimensional picture of the cone like this, the point is that the green plane has the same slope as the edge of the cone. Then we have a special curve called a parabola. If we make our plane steeper still, then it's going to cut the top of the cone and it's going to cut the bottom cone. And we get the cut, or the intersection between the two, is going to be a type of curve called a hyperbola. In this chapter, we're going to be studying ellipses, parabolae, and hyperbolae. For parabolas or parabolae, where do we see them? We might see them in the motion of a bouncing ball. If we look at a suspension bridge, we look at the curve that the ropes lie in. This curve is almost, not exactly, but almost a parabola. Why is it not exactly a parabola? If you become a bridge architect, you can ask your engineer to explain why it's slightly different. They will explain it's due to the weight of the bridge hanging down on the rope. It's not exactly a parabola. But for purposes of drawing bridges, we can assume that it's a parabola. And we see parabolas on satellite dishes. If we did a line across a dish like this curve would be a parabola. To describe a parabola, we need 2 things. We need a point, which we call a focus, and we need a line, which we call a directrix. This blue curve is my parabola. The focus, I'm assuming, is at the point 0p, and the directrix, I'm assuming, is the line y is equal to minus p. Let p be any point on the parabola. It might be the point I've drawn, it might be this point, it might be this point, it might be this point, any one of these points. and we say that this has coordinates x, y. We can measure the distance from the focus to our point P, and we can measure the distance from our point P down to the directrix. We can imagine a vertical line from the point meets the directrix at a point Q, which then has the coordinates x minus P. For a parabola, there's a very important rule. A parabola must satisfy that the distance from P to F is the same as the distance from P to Q. This is the definition of a parabola. The point xy lies on the parabola if and only if the distance from P to F is the same as the distance from P to Q. Using this, we can find an equation for a parabola. There's a lot of maths here. I'm going to go through this slowly. PF, the distance between P and F, using our formula from last week, or using Pythagoras, we know is the square root of x minus 0 squared plus y minus p squared, or the square root of x squared plus y minus p squared. We can do the same thing for the distance between P and Q, and we find it's y plus p. Or we can go back to the picture. We can look at this distance. This distance is y. This distance is p. So the distance between P and Q should be y plus p. And it is. Now we're told that these two distances must be the same. If we have a parabola, then the distance from P to F must be the same as the distance from P to Q. So the square root of x squared plus y minus p squared must be the same as y plus p. If we rearrange this equation, cancel the terms, we end up with the standard equation for a parabola. X squared is equal to 4py, which I will leave for you to check. This was our parabola that we looked at before. Our equation is x squared is equal to 4py. The focus is at the point 0p, and the directrix is the line y is equal to minus p. Perhaps we have a different parabola. Instead of a parabola which is curving upwards, perhaps we have a parabola which is curving downwards. We could do everything the same, or we could just say, replace every y by minus y. We get the equation x squared is equal to minus 4py, minus because we turned the picture upside down. The focus is now at the point 0 minus p, and the directrix is at y equal to p. Or let's suppose we rotate our picture and we have a parabola which is curving to the right. Imagine we take the original equation and we swap the places of x and y. So instead of x squared is equal to 4py, we swap x and y and we get y squared is equal to 4px. The focus is at p0 and the directrix is x is equal to minus p. Or we can have one which is curving to the left. Place every x by minus x. We get y squared is equal to minus 4px. Focus is at minus p0, and now the directrix is at x is equal to p. Now that we know this, we can answer this example. Find the focus and the directrix of the parabola y squared is equal to 10x. We have the equation y squared is equal to 10x. This looks like y squared is equal to 4px, where p is equal to 2.5. As soon as we know p, we can find the focus and the directrix. The focus must be at 2.50, and the directrix must be x is equal to minus 2.5. Or we can go the other way. Let's suppose we're told the focus and we're told the directrix, and we're asked to find the equation for the parabola. We're told that the focus is at 0 minus 10. So straight away we can say therefore p is equal to 10. And looking at the pictures, you see we must have the equation x squared is minus 4py. So the answer to this question must be x squared is equal to minus 40y. Ellipses. Where do we see ellipses? If we had a piece of string which was attached to our paper using 2 pins, and if we used a pencil to draw around, we would have an ellipse. Ellipses are the orbits of the planets in the solar system, and we see them in architecture sometimes. For example, this building in Denmark has an ellipse on top of it. To describe an ellipse, instead of one focus on Directrix, we need 2 foci. Focus is one of these unusual words where the plural is different than we would expect. We can have 1 focus or 2 foci. Let's suppose we have a focus at minus C0 and another focus at C0. Again, let P be any point on the ellipse, any point anywhere around here. We can measure the distance from P to the 2 foci. And the rule for an ellipse, and that comes from this picture, because the string is always of the same length. The rule for an ellipse is that the sum of these 2 distances must be a constant. And for the constant, we use 2a, as you will see why later. We use this as the definition. A point xy is on the ellipse if and only if the distance from P to F1 plus the distance from P to F2 is always the number 2a. As we did before, we can find an equation. I'll leave this for you to check, for you to fill in the details. If we rearrange this, we get x squared over a squared plus y squared over a squared minus c squared is equal to 1. We can simplify this a little bit if we use a new name for a squared minus b squared. Introduce a new number called b, which is equal to the square root of a squared minus c squared, and we get the standard equation x squared over a squared plus y squared over b squared is equal to 1, where it's important to note, because of the way we define b to be the square root of a squared minus c squared, b must be a smaller positive number than a. Here is a picture of this ellipse. We have the equation x squared over a squared plus y squared over b squared is equal to 1, where 0 is less than b is less than a. Our ellipse crosses the x-axis at a and minus a. It crosses the y-axis at b and minus b. The distance from the center to each focus is c, or rearranging the equation on the previous page, the square root of a squared minus b squared. The foci are minus c0 and c0, and the points where it crosses the x-axis, the longer axis, are minus a0 and a0. Note that the vertices, the foci, and the center are all on the same line. We might take this ellipse and we might rotate it by 90 degrees. Then we have the equation x squared over b squared plus y squared over a squared is equal to 1. Why is it now b first and a second? It's because I always want to use a for the bigger number and b for the smaller number. Then the center to focus distance stays the same, square root of a squared minus b squared. The foci are 0 minus c and 0c. And now the vertices are on the y-axis at 0 minus a and 0a. For example, The ellipse x squared over 16 plus y squared over 9 is equal to 1. A squared is 16, so A must be 4. B squared, the smaller number, is 9, so B is equal to 3. After we know A and B, we can calculate the center to focus distance, in this case, square root of 7. The center is at 0, 0. The foci are at minus 7, 0, so minus root 7, 0 and root 7, 0. And the vertices are at minus 4, 0 and 4, 0. It's minus A0 and A0. Next one, the ellipse x squared over 16 plus y squared over 25 is equal to 1. Two numbers, 16 and 25. We take the bigger number for a squared, so a must be 5, and the smaller number we take for b squared, so b must be 4. Then we can measure the center to focus distance. We can calculate the center to focus distance is 3. The center is 0, 0 again. The foci are 0, minus c and 0, c, or 0, minus 3 and 0, 3. And the vertices are 0, minus a and 0, a, or 0, minus 5 and 0, 5. Hyperbolas. Where do we see hyperbolas? One example would be on a cooling tower. The curve on the edge of a cooling tower is a hyperbola. Or this building in Japan is constructed using two hyperbolas or hyperbolae. Again, we need two foci, and again, we're going to say they are minus C0 and C0, but there's a different rule. This time, instead of plus in the rule, we have minus. And because we don't know which one of these distances is going to be bigger, depending on if we're on the left curve or the right curve, we're going to need to put absolute values around it. The rule for a hyperbola is that the absolute value of the difference between the distance from P to F1 and the distance from P to F2 is always the same number. It's always equal to 2a. And as before, the vertices are minus a and a. As before, we could start by writing down the distances, rearranging them, introducing a new number, b, and we would end up with the standard equation, which in this case is x squared over a squared minus y squared over b squared is equal to 1. For an ellipse, we had a plus here. This is almost the same, but instead of a plus, we have a minus sign. One more difference. For an ellipse, we said that a always needed to be a bigger number than b. For hyperbola, we don't care which number is bigger. Maybe a is bigger than b, maybe b is bigger than a. It doesn't matter. To recap, we have the hyperbola x squared over a squared minus y squared over b squared is equal to 1. The center to focus distance. For an ellipse, it was square root of a squared minus b squared. For hyperbola, almost the same, except instead of minus, we have plus. The foci are minus C0 and C0. The vertices are minus A0 and A0. We can rotate this by 90 degrees to get this equation. All I've done here is I've swapped the positions of x and y. So it's now y squared over a squared minus x squared over b squared is equal to 1. The center to focus distance stays the same. The foci are now on the y-axis, as are the vertices. For example, the hyperbola x squared over 4 minus y squared over 5 is equal to 1. Doesn't matter if a is bigger than b or b is bigger than a. For a hyperbola, the first number we say is a squared, so a must be 2, and the second number we say is b squared. So here, b must be the square root of 5. The center is always at 0, 0. The center to focus distance we can calculate must be 3. Because we're doing a squared plus b squared, we don't care if a is bigger or b is bigger. For an ellipse, we have a minus sign here, so we had to have that a was bigger than b. But this time, it doesn't matter. As soon as we know c, we can write down the foci. As soon as we know a, we can write down the vertices. One more example. The hyperbola y squared over 9 minus x squared over 16 equal to 1. Again, the first number is a squared, so a is 3. Second number is b squared, b is equal to 4. Center 0, 0. Center to focus distance is 5. Foci are at 0 minus c and 0 c. Vertices are at 0 minus a and 0 a. Why are we interested in ellipses, parabolas, and hyperbolas? Because they're useful in architecture and engineering because of their reflective properties. First, a parabola. A parabola has the special property that if we have rays which start or finish at the focus, if these are reflected off the parabola as if the parabola is a mirror, then these rays will exit the parabola as as parallel lines. This is useful, for example, in a car headlight. We would put the light at the focus, and then we would have a mirror in the shape of a parabola. The light would emit from the light bulb, would reflect off the parabolic mirror, and would leave the car in parallel lines. Or we might use the same property on a satellite dish. So imagine we have some satellite up in orbit, which is sending its signal down. The signal bounces onto the parabolic satellite dish, and then because of the shape of the dish, it's reflected to the focus of the parabola. We put the receiver or the sensor at the focus. Here's an example from architecture. This is a picture which was taken in San Francisco. There is a concrete dish in the shape of, so with a parabolic shape. There is a seat which sits so that the person sits with their head at the focus of the parabola. And then far off to the right of the picture, there's another dish, another seat, another person sitting on the seat with their head at the focus of the parabola. And then what happens is one person talks, the sound of their voice reflects off the dish all of the way across this place, wherever it is, onto the other dish, and then it's reflected to the person's ear. These two people, which are quite a long way apart, can talk to each other because their voices echo off the dishes to each other. For an ellipse, the rule is that rays which start at one focus are bounced off the ellipse to the other focus. So, for example, if we had two people in a crowded room, and if the two people stood at the foci of the ellipse, these two people could talk to each other because their voices would bounce off or echo off the walls of the building to each other. Here's another picture. If we had, say, a subway tunnel shaped like an ellipse. People on opposite platforms, if they stood in exactly the right place, could talk to each other. Because architects know this, sometimes architects build elliptic rooms and they make sure that somebody sits right on the focus. Here's perhaps the most famous elliptic room in the world. For hyperbola, the rule is that if a ray is shown towards the focus, so towards one focus, it's reflected towards the other focus. Of course, usually a parabola has two parts, but I'm only drawing one in this picture. If we imagine light or sound or something that's shown towards the top focus, it bounces off the hyperbola towards the bottom focus. Where is this useful? This could be useful in, for example, a telescope. This is a very simple telescope. This telescope just has two mirrors. On the left, we have a parabolic mirror. On the right, a hyperbolic mirror. The light comes into the telescope in straight lines. It shines onto the parabolic mirror, and then the parabolic mirror reflects the light towards the focus of the parabolic mirror. You then build a second mirror, this time using a hyperbolic curve, which has the same focus as the parabola. Using the properties of a hyperbola, the light is then reflected towards the other focus of the hyperbola. So just using these two mirrors, we can refocus all of the light to one of the foci of the hyperbola. Our final chapter for today is three-dimensional Cartesian coordinates. Time to start thinking in 3 dimensions. In 3-dimensional coordinates, we need 3 axes in this case, and we use an x-axis, a y-axis, and a z-axis. The point where these 3 axes cross is called the origin, with the point we say has coordinates 0, 0, 0. And then we can describe the point in space of any point using 3 numbers, an x-coordinate, a y-coordinate, and a z-coordinate. We always draw the axes in one particular way. Imagine you hold your left hand in the air like this. Let's suppose you hold your fingers so that your middle finger is at 90 degrees from your index finger and your thumb is at 90 degrees to both of these points. We draw the axes so that our middle finger points along the x-axis direction, our index finger points along the y-axis direction, and our thumb points along the z-axis direction. Anytime you see a picture like this, imagine holding up your left hand, rotating your hand so that your fingers line up with the axes. X equal to a number is a plane. For example, x equal to 0 is the yz plane, y equal to 0 is the xz plane, and z equal to 0 is the xy plane. Z equal to 5. All of the points where the z coordinate is equal to 5. So x can be any number, y can be any number, but z has to be 5. We would have a horizontal plane, which I've tried to draw here in blue. Or suppose we insisted that y is equal to 3. If we let x be any number and z be any number, but we said y must be equal to 3, we would get this vertical green plane. These two planes intersect in a line, which I've drawn here in red. The red line is the line where y is equal to 3, z is equal to 5, and x can be any number. For example, which points x, y, z satisfy x squared plus y squared is equal to 4 and z is equal to 3? First of all, z equal to 3. We know that z equal to 3 is a horizontal plane of height 3 above the origin. And we also recognize the equation x squared plus y squared is equal to 4. This is the equation of a circle of radius 2. Let's put these two ideas together. In blue, I've shown the plane z is equal to 3. Inside this plane, we have a circle of radius 2. So imagine a red circle which is hovering in space at height 3. The set of all points in three-dimensional space, that's any real number x, any real number y, any real number z. We've got 3 lots of the real numbers, so we call this R3. We can measure the distance between any 2 points in R3 using this formula. The distance from P1 to P2 is the square root of x squared minus y1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Same idea that we used in two-dimensional space. So, for example, we can measure that the distance between 215 and minus 230. Using this formula, we get 3 square root of 5, which is a good way to write the answer. What is a sphere? A sphere is the set of all points in the plane where the distance from the surface to the sphere to some point is constant. If we say that the center of the sphere is the point P0, then any point on the surface of the sphere must satisfy the rule that the distance from P0 to P is always the same number. In this case, let's say A. From our formula for the distance between any 2 points, square both sides, we find the standard equation for a sphere of radius A centered at the point x0, y0, z0. The equation is x minus x0 squared plus y minus y0 squared plus z minus z0 squared is always equal to the number a squared. For example, find the center and the radius of the sphere x squared plus y squared plus z squared plus 3x minus 4z plus 1 is equal to 0. The first thing we need to do is we need to put our equation into the standard form. Here's the standard equation. It's x minus something squared plus y minus something squared plus z minus something squared is equal to something. But we don't have this. We have x, y, and z, and a 3x and a 4z and a 1, all on the left. We need to rearrange our equation so that it looks like the standard equation. First thing I'm going to do is I'm going to group all of the x terms together, all of the y terms together, and all of the z terms together. And the number I'm going to move over to the right. So I have x squared plus 3x plus y squared plus z squared minus 4z is equal to minus 1. Now this is not quite what we want yet. I want x minus something squared. And to make that, I'm going to add on and subtract something. Because I have a 3, I'm going to divide 3 by 2 and then square it. I'm going to do 3 over 2 and then I'm going to square it. I'm going to add on 9 over 4, and then I'm going to subtract the same number. Because we're adding on 9 over 4 and then subtracting the same number, our equation doesn't change. Y squared, we can just leave as it is. For the z minus 4 squared, we need to also add something and subtract the same thing. The rule is we take out minus 4, we do minus 4 divided by 2, and then we square it. And we get plus 4. So I do plus 4, and then I subtract the same thing. So far there's been no changes. Minus 9 over 4 and minus 4. These are numbers. We can move these both over to the right. And we have x squared plus 3x plus 9 over 4 plus y squared plus z squared minus 4z plus 4 is equal to all of the numbers. Why am I doing this? Why did I add on something and then subtract it? Because I can then factorize this to x plus 3 over 2 squared plus y squared, and then instead of z squared minus 4z plus 4, we can factorize this to z minus 2 squared. Whichever number we have on the 3x here, or the 4z, we should have half of that number just here. So plus 3 over 2 instead of plus 3, and minus 2 instead of minus 4. Now that we've done this work, now that we've done this calculation, we can read off the information that we need. If I go back, the center is x0, y0, z0, where x0, y0, and z0 are these three numbers inside the equation. What numbers do we have? We have 3 over 2 here, but it's plus instead of minus. So we want minus 3 over 2. It's just plus y squared. There's no number here, so we would have 0. And then in the z coordinate, we have minus 2. So we just read off z0 must be 2. For the radius, we look at the number on the right. 21 over 4 must be equal to a squared, or to say it another way, a must be the square root of 21 over 4, or square root of 3, square root of 7 divided by 2. And that's the answer to this problem. Next week, again, we're going to talk about 3 chapters. We will talk about vectors, and using vectors, we will talk about the dot product and the cross product. That is the end of this week's lesson. Do you have any questions?